Stoichiometry. This is the branch of chemistry that deals with the quantities of materials consumed and produced in a chemical reaction, meaning the mass, or moles, of reactants that react in a chemical reaction versus the mass in grams, or the moles, of products produced in this reaction. Molar mass comes from the periodic table. It is rounded to the nearest hundredth, which is 2 decimal places. And this is the mass of 1 mole of a substance. Let's look at hydrogen and oxygen from the periodic table. In order to round to the nearest hundredth, which is the second decimal place, you sometimes have to look at the third to determine whether or not that digit will round up. So for hydrogen, that would be 1.0 and then 1. The 8 rounds to 0 up to a 1. And that is grams for every 1 mole of hydrogen. For oxygen, the second decimal place is a 9. The third is also a 9, which rounds the 9 up. So there's kind of a chain reaction here until this rounds up to the whole number, 16.00 grams of oxygen per 1 mole of oxygen. Now technically, both those are diatomic, so it would actually be double of that. Now as far as figuring out the molar mass of a compound, such as water, you have to add the masses of each element. In that compound, there are 2 hydrogen and 1 oxygen. So you'd have to add 1.01 for the hydrogen, and then 1.01 again for the second hydrogen, and then the 16.00 for the oxygen, for a grand total of 18.02 grams of water for every 1 mole of water. That is molar mass. We use the molar mass in the stoichiometry problems to convert from the number of grams to the number of moles. A balanced chemical equation is essential to stoichiometry problems. The coefficients, the numbers placed before the compounds, indicate the number of each compound. In this equation, it says that 2 moles of atmospheric hydrogen will react with 1 mole of atmospheric oxygen to produce 2 moles of water. In all balanced chemical equations, there are reactants, meaning the substances that go into the reaction, and the products, those substances that are produced. We can use the coefficients to establish mole ratios. For example, there are 2 mole of H2, and I can relate that to the 1 mole of O2 as demonstrated by this reaction. There are other possible combinations. For example, 2 moles of water compared with 2 moles of hydrogen. The mole ratio is a step that's present in all stoichiometry problems. When there is more than one reactant in a chemical reaction, it is typical that one is the limiting reactant, meaning it would run out first, and the other would be referred to as the excess reactant, meaning it's in abundance. Look at this graphic. It demonstrates that if the compound is formed by bonding one of the blue particles to one of the red particles, that the blue particle is the limiting reactant, because after it makes the first compound, no more can be made because there are no more blue remaining. And it doesn't matter how many red you have. The red would represent the excess. The mass-to-mass stoichiometry problems we've been working are 4-step problems. They always follow the same pattern. The given information is first. The second step is the molar mass. This information is obtained from the periodic table and is the molar mass of the given substance. In this example, the given substance was H2. So 1 mole of H2 would have a mass of 2.02 grams. Step 3 is the mole ratio. All stoichiometry problems contain a mole ratio step. This is where the coefficients in the equation, the balanced equation, are used so that we can change from talking about hydrogen to talking about the other substance, in this case ammonia. And the fourth step is another molar mass, again from the periodic table, but this time instead of it being the molar mass of the given compound, like hydrogen, it's the molar mass of the compound we're trying to solve the problem about, and in this case that will be ammonia. Again, molar mass is the mass of 1 mole of that substance. Notice that molar mass in both situations is given to 2 decimal places, 2.02, 17.04. Molar mass is always expressed to 2 decimal places. Study this pattern because it's the same every time. Why don't we work some sample problems? The first step in stoichiometry is always to balance the equation. Find something that is different on the 2 sides of the equation. For example, there are 2 nitrates on the right, but only 1 nitrate on the left. So if we put a coefficient of 2 in front of silver nitrate in the reactants, we have the same number of nitrates on both the left and the right. By doing this, we affect the number of silver. We now have 2 silver expressed on the left, but only 1 on the right. To reconcile that, we'll put a 2 in front of silver. Copper is 1 on both sides. So this is the balanced chemical equation. Next, write down the given information. If our given information is 78.7 grams of silver, we will have 4 steps. The next will be to look up the molar mass of silver on the periodic table, and that would be the amount of 1 mole of silver. That is 107.87 grams of silver expressed to 2 decimal places, or the nearest hundredth. The third step is the mole ratio step, where we want to change, talking about moles of silver, to moles of whatever substance, let's say copper. We would look at the balanced chemical equation and we would use the coefficients of copper and of silver to create this mole ratio. No number implies a 1. And then the final step is another molar mass step. If you notice, the units so far have been cross-canceling, upper left to bottom right. So we want to continue that same pattern and have the next one on the bottom be moles of copper in anticipation of those canceling. The final unit will be the unit of our answer. So we need to look on the periodic table and find out what the mass of copper is for every 1 mole of copper. Expressed to the nearest hundredth, that would be 63.55. As far as the math goes, as you input this into the calculator, you'll want to multiply everything across. So that would be 78.7 times 1 times 1 times 63.55. And then everything on the bottom will divide by. Divided by 107.87, divided by 2, divided by 1, in order to achieve the final answer, which would be stated as the grams of copper. Here's another example. Of course, we're going to begin with the balanced chemical equation. So we need to find something that is different between the two. I notice there are 3 chlorines on the left and 2 chlorines on the right. I like to resolve that first, personally. Whenever there is a 3 and a 2, just swap those. So 2 times 3 is 6, 3 times 2 is 6, which of course sets off a chain reaction. Now I'm saying that I have 3 moles of copper. So I need to go back on the reactant side and make sure that there were 3 moles of copper. This implies there are 3 sulfates, but on the right-hand side there are 3 sulfates, so that's balanced. And then finally, this says there will be 2 aluminum, and there are 2 aluminum. So this is the balanced chemical equation. We always start with the given, which in this case is 5.94 grams of copper 2 chloride. This will be a 4-step equation. In step 2, we will add up the mass of copper and 2 chlorines to get the molar mass of 1 mole of copper 2 chloride. Step 3 is the mole ratio step. So we're going to change from moles of copper chloride to some other substance, let's say moles of aluminum chloride. We use the coefficients in front of these 2 compounds in the equation to be the numbers in this mole ratio step. And then finally, since we want to express our answer in grams of substance, in this case aluminum chloride, we would need to add an aluminum and 3 chlorines to get the answer of grams of aluminum chloride. In the end, you'll want to multiply across the top, divide across the bottom, in order to get the final answer. Now for the limiting reactant problem, we've simplified this down to a mole-mole step. Always start with a balanced chemical formula. I like to balance my carbons first in a combustion reaction such as this, and next the hydrogen. Remember that in order to balance the oxygen, it's in 2 locations in the products, and those add together. We have 5 times 2 oxygen, that's 10, plus 6 oxygen, that's 16. Since in the reactants that's O2, we need half of 16, which is 8. 8 times 2 is 16. Now the equation is balanced. We work these problems 2 times. Each time we start with the given information of each of the reactants, and we want to identify which of these 2 reactants is in excess and which one is the limiting, or the one that controls how much product can be produced. In anticipation of needing the moles of reactant to cancel, we put that on the bottom of the second step. Now we want to identify how much product can be made from each reactant. So we need to pick a product and stick with it. Since I know the mass of water off the top of my head, which is 18.02, let's go with that. So we are going to put moles of water in both positions at the top for each trial. That way it'll be the same. We need these coefficients here to fill in the quantities in the mole ratio. So that's a 6 for moles of water, a 1 for moles of pentane, and an 8 for moles of oxygen. That comes from the balanced chemical equation. Now we multiply across the top, divide across the bottom. One of these answers will be larger than the other. You'll notice that the unit for both trials is the same, moles of water, because as we worked these, the units for each of the reactants canceled themselves out. This was done purposely so that we can see which reactant, pentane or oxygen, will give us the most product, in this case, the most water. We have enough oxygen to make quite a bit of water. Therefore, the pentane is the limiting reactant because we only have enough to make 27 moles of water, meaning the oxygen was in abundance. We had excess oxygen. And that's how you work these limiting reactant problems. Review these again, these steps, so that you can recreate this kind of work on your test. Good luck.